In this lecture, I'll talk about programming with Spark, the Spark abstraction resilient distributed data sets, how you create an RDD, and the transformations and actions that you can perform on RDDs, and then I'll talk about the Spark programming model. In this course, we're using the Python programming interface to Spark called PySpark. PySpark provides an easy-to-use programming abstraction in parallel runtime. The way to think about it is you just simply say, here's an operation, run it on all of the data. To make all of this work, RDDs are the key concept. A Spark program consists of two programs, a driver program and a workers program. The driver's program runs on the driver machine, and the worker programs run on cluster nodes or in local threads. And then RDDs are distributed across the workers. The first thing a program does is to create a Spark context object. This tells Spark how and where to access a cluster. The PySpark shell and Databricks Cloud automatically create the SC variable for you. In IPython and other programs, you have to use a constructor to create a new Spark context. You then use the Spark context to create RDDs. As a reminder, in the labs, we create the Spark context for you, so you don't have to worry about it. The master parameter for a Spark context determines which type and size of cluster to use. And there are two choices, local clusters and remote clusters. For local, you can either choose to run Spark with just one worker, no parallelism, or you can run it with k worker threads, where ideally you want to set k to be the same as the number of cores that you have in your machine. To work with clusters, you can either connect to a Spark cluster or to an Apache Mesos cluster. In the labs, we set the master parameter for you, so you don't have to worry about this parameter. Resilient distributed data sets are the primary abstraction in Spark. They are immutable once you create an RDD. You cannot change it. You can transform it, you can perform actions on it, but you cannot change an RDD once you construct it. Spark tracks lineage information to enable the efficient recomputation of any lost data if a machine should fail or crash. It also enables operations on collections of elements in parallel. Now you can construct RDDs by parallelizing existent Python collections, such as lists, or by transforming an existing RDD, or from files in HDFS or any other storage system. A programmer specifies the number of partitions for an RDD, and there's a default value that's used if you don't specify the number that you want to be used. Here we have an example of an RDD that's split into 5 partitions. The more partitions that you split an RDD into, the more opportunities you have for parallelism. So this RDD is split into 5, and those are placed onto 3 worker machines. Since there's only 3 worker machines, some of the worker machines have 2 partitions and one has 1 partition. There are 2 types of operations you can perform on an RDD, transformations and actions. Transformations are lazily evaluated. They're not computed immediately. A transformed RDD is executed only when an action runs on it. You can also persist or cache RDDs in memory or on disk. To work with RDDs, you first create an RDD from a data source, a file or a list. You then apply transformations to that RDD. So examples are map and filter. You then apply actions to that RDD. Examples are collect and count. So here we have a figure that shows, starting with a list, we parallelize that list. That creates an RDD. We then filter that RDD, creating a new filtered RDD. Then we do a map transformation that maps that RDD to a new mapped RDD. And finally, we perform a collect action, which now causes the parallelize, the filter, and the map transformations to actually be executed and return a result back to the driver machine. Here are 2 reference URLs for working with Spark. The first is a programming guide, and the second is the PySpark API. These are very good references when you're developing Spark applications. The programming guide gives you some best practices and also cautions you against doing certain things. The Python API is very useful if you're wondering, is there a transformation to do a particular operation? And also, what are the different parameters that a given transformation or action takes? So let's look at some examples of creating an RDD. Here we create an RDD from a Python list. So we start with the list data, and then we use sc.parallelize to create an RDD. Now, no computation actually occurs when we run the sc.parallelize operation. All that occurs is Spark records how to create an RDD that has 4 partitions from our list. Here, we can look at what happens when we use sc.text file with an actual file instead. So we can use a file that comes from HDFS, from a text file, from Hypertable, Amazon S3, Apache HBase, sequence files, or any other Hadoop input format, or even a directory or wildcard. Again, all that will happen is Spark will record that we want to create an RDD, in this case with 4 partitions, from the file readme.md. Now, what actually happens when we do something like sc.text file? Well, we tell Spark that we want to create an RDD that's distributed in 4 partitions. Each element of that RDD is going to be a line from the input file. And again, lazy evaluation means that no execution happens right now. All that happens is Spark records how to create the RDD from that text file. Spark transformations enable us to create new data sets from an existing one. Again, we're using lazy evaluation, so that means that results are not computed right away. Instead, what happens is Spark remembers the set of transformations that are applied to a base data set. It can then optimize the required calculations and automatically recover from failures and slow workers. The way to think about this is we're creating a recipe for creating a result. So let's look at some examples of transformations. There's the map transformation, the filter, distinct, and flat map transformations. The map transformation returns a new distributed data set that's formed by passing each element of the source through a function. Filter returns a new data set that's formed by selecting those elements of the source on which the function returns true. And the distinct transformation returns a new data set that contains the distinct elements of the source data set. The flat map transformation is similar to map, but each input element can be mapped to 0 or more output elements. So this means that your function should return a sequence rather than a single item. Let's review Python lambda functions. These are small anonymous functions that are not bound to a name. So here we have lambda a comma b colon a plus b. This returns the sum of its 2 arguments, a and b. You can use lambda functions wherever function objects are required, but they're restricted to a single expression. Let's look at the transformations that we just talked about. So here we start with creating an RDD using sc.parallelize of a list, the list 1, 2, 3, 4. Then we apply the transformation map, and we pass in a lambda function that will double each element. Now, Spark turns this function literal into a closure and passes it automatically to the worker. So the code in black runs at the driver, the code in green runs at individual workers. So what will happen here is it'll take the RDD 1, 2, 3, 4, and it'll transform it into 2, 4, 6, 8. Now again, nothing actually happens until an action is performed, but this is part of the recipe that we're constructing. Now alternatively, we could have used a filter transformation. Here, the lambda function will return true if the element modulo 2 equals 0. So this will take our RDD of 1, 2, 3, 4 and return elements 2 and 4. So we construct a new RDD consisting of 2 and 4. The last transformation on this slide is the distinct transformation. So we start by parallelizing the list 1, 4, 2, 2, 3, and then we take and pass that to the distinct transformation. That will give us a new RDD that only contains the distinct elements of the input RDD. So this creates a new RDD with only 1, 4, 2, and 3. Those are the unique elements of the input RDD. Here's another example of a transformation, the map transformation. So we pass in an RDD that we created using SC parallelize with 1, 2, 3, and that is then passed to a map with a lambda function that will return x and x plus 5 as each element. So this takes, as a list, this takes that RDD that was 1, 2, 3 and creates a new RDD where each element of the RDD is a list. So we have now first element of the RDD is 1 and 6, second element is 2 and 7, and the third element is a list of 3 and 8. Now let's compare this to what happens when we use flat map. When we use flat map, we would create the same RDD, but then it flattens that RDD and takes each list and turns it into individual elements. So instead, we end up with the RDD consisting of the elements 1, 6, 2, 7, 3, and 8. So let's look at what happens when we transform a text file-based RDD. So here, we create a new RDD lines from a text file, and this is going to create an RDD with 4 partitions. We then filter out lines that are comments. And so here we're passing in a function instead of passing in a lambda. And the function here is called isComment. And it doesn't matter what the function is actually doing, but what we'll say is if the line is a comment, we want it removed from the RDD. So we'll create a new RDD, comments, that contains only those elements from lines that are not comments. Now, lazy evaluation means that nothing is actually going to happen right now. Spark instead will save a recipe for how it's going to transform the source. Spark actions cause Spark to execute the recipe to transform the source. They're the mechanism for getting results out of Spark. Here are 4 Spark actions. The first action is reduce. Reduce aggregates a dataset's elements using a function. That function takes 2 arguments and returns 1. It has to be commutative and associative so that it can be computed correctly in parallel. The take action returns an array with the first n elements, and the collect action returns all of the elements of the RDD as an array. So you have to make sure that all of that data will fit in the driver program. Take ordered returns n elements ordered in ascending order or as specified by the optional key function. So let's look at some examples. We start with parallelizing a list, 1, 2, 3, and then we use the reduce action. We pass in a lambda function that will multiply the 2 elements together. So this will multiply all of the elements of the list together to produce a single value, the value 6. 1 times 2 times 3. The take action will return the first 2 elements of the RDD. So in this case, it returns 1 and 2 as a list at the driver. Collect returns all of the elements of the RDD as a list at the driver. So in this case, that's 1, 2, 3. And again, always be careful when using collect to make sure that the results will actually fit in the driver's memory. Here, we apply the parallelize option to the list 5, 3, 1, 2. This returns an RDD containing 5, 3, 1, and 2. We then use take ordered to take the first 3 elements. We pass in a key function that will multiply an element by -1. So instead of take ordered returning the first 3 elements in increasing value, it will return them in decreasing value. And so we'll get back 5, 3, and 2 as a list at the driver. Let's look at the example that we created before. So here we have the creation of an RDD lines from a text file with 4 partitions. Nothing happens when we actually do that until we execute an action. The action we're going to execute in this case is the count function, which returns a count of the number of elements in an RDD. So when we run the command print lines.count, that will cause Spark to read the data from the text file, to sum the number of lines per partition, and then to combine those sums in the driver. And we'll find out how many lines are in our program. Now, if we add another transformation, in this case, a filter transformation, that's going to create create an RDD that contains the lines that are comments. And then we want to see how many comments lines there are. We can do comments.count. This is going to cause Spark to recompute lines. It will reread all of the data from that text file again, sum within the partition the number of lines, so the number of elements, and then combine those sums in the driver. To avoid having to reload the data, we can add the cache directive to the lines RDD. So here we use lines.cache. This tells Spark to save that lines RDD so that we don't have to recompute it each time we want to use it. So now what will happen is the first time when we do lines.count, that will cause us to read the text file into memory. Then we'll count the number of lines, sum that across each of the partitions, then combine that total in the driver. Now, when we run the filter, lines.filter, to create the comments RDD, instead of that having to read from disk, it will read from memory. So it'll run much, much faster. The lifecycle of a Spark program is that you first create RDDs from some external data source or parallelize a collection in your driver program. You then lazily transform these RDDs into new RDDs. You cache some of those RDDs for future reuse, and you perform actions to execute parallel computation and to produce results. Similar to MapReduce, Spark supports key value pairs for RDDs. Each element of a pair RDD is a pair tuple. So here's an example where we apply the SE_parallelize operation to a list consisting of two pairs. The first pair is 1, 2. The second pair is 3, 4. This creates a new RDD that consists of two elements, the first element being the pair 1, 2, and the second element being the pair 3, 4. Now, some of the key value transformations that we can perform include the following. Reduce by key, which takes an RDD and returns a new distributed RDD of key value pairs where the values for each key are aggregated using the given reduce function. And that reduce function has to be of the type takes two values and returns one value. The second key value transformation is sort by key. This returns a new data set of key value pairs that's sorted by keys in ascending order. And the third key value transformation that we're going to look at is group by key. This returns a new data set consisting of key and iterable value pairs. So let's look at some examples. So the first example is a reduce by key example. So we start by parallelizing a list consisting of three tuples, 1, 2, 3, 4, and 3, 6. We then call the reduce by key transformation with a lambda function that will sum the two values. This produces a new RDD consisting of two elements. The first element is the tuple 1, 2. The second element is the tuple 3, 10. The 10 came from taking the two tuples 3, 4, and 3, 6 and combining the values using the lambda function, which summed them up, giving us the value 10. The second example is a sort by key example. Here we create an RDD by parallelizing three tuples, 1 and the character A, 2 and the character C, and 1 and the character B. Now when we invoke sort by key, what we end up with is a new RDD that consists of the elements a tuple of 1 and A, a tuple of 1 and B, and a tuple of 2 and C. The third key value transformation that we'd like to look at is a group by key. So using that same RDD from the last example, the tuple 1A, 2C, and 1B, when we apply the group by key transformation, what we end up with is a new RDD that contains two elements. The first element is the tuple 1 and an iterable of A and B. And the second element is the key 2 and an iterable of C. You have to be very careful when using group by key, as it can cause a large amount of data movement across the network. It also can create very large iterables at a worker. Imagine you have an RDD where you have a million pairs that have the key 1. All of the values will have to fit in a single worker if you use group by key. So instead of group by key, consider using reduce by key or a different key value transformation. Spark automatically creates closures for functions that run on RDDs at workers and for any global variables that are used by those workers. Now, one closure per worker is sent with every task, and there is no communication between workers. And any changes that you make to the global variables that are at the workers are not sent to the driver or to other workers. Now consider the following use cases. What if we have an iterative or a single job that has a large global variable? So this would result in sending a large read-only lookup table to the workers, or sending a large feature vector in a machine learning algorithm to the workers. Or what if we want to count events that occur during job execution? So for example, how many input lines were blank, or how many input records were corrupt? The problem we have is that these closures that are automatically created are sent or resent with every job. So for an iterative job with a large global variable, we'll be sending that large global variable with every single job to every single worker. It's also very inefficient to continually send large amounts of data to each worker. And closures are one way from the driver to the worker. So how can we count events that occur at a worker and communicate that back to the driver? Well, to do this, PySpark provides shared variables and two different types. The first is broadcast variables. These enable us to efficiently send large read-only values to all of the workers. They're saved at the workers for use in one or more Spark operations, and it's like sending a large read-only lookup table to all of the nodes. The second shared variable type is accumulators, and they allow us to aggregate values from workers back to the driver. Now, only the driver can access the value of an accumulator. For the tasks, the accumulators are basically write-only. And we could use this as an example to count errors that are seen in an RDD across workers. Broadcast variables allow us to keep a read-only variable cached at a worker. We can send it to the worker only once instead of having to send it with each task that we perform at that worker. As an example, we could efficiently give every worker a large data set or table. Now, usually broadcast variables are distributed using very efficient broadcast algorithms. Using broadcast variables is very straightforward. At the driver, you simply use Spark context.broadcast to specify the broadcast variable. And at a worker, in the code that's automatically passed via a closure, you simply refer to that broadcast variable with .value. Here's an example of using a broadcast variable for country code lookup for ham radio call signs. So we have an RDD, contact counts, that contains a list of call signs and the number of times that we've seen each call sign. So it's a pair of call sign and a count. And we want to look up the country code associated with that call sign. So we create a table called sign prefixes that contains this information. We then create a function, process sign counts, which will take in one of these pairs of a call sign and a number of times that it's been seen, along with that table, sign prefixes, and we'll look up the country code from the first element of the pair, the call sign, and then return a pair consisting of the country and the number of times that we've seen that call sign. Now, we can apply this to our contact counts RDD using a map function where we pass in this function that we just defined, process sign counts. What that'll do is when that runs, Spark will automatically create a closure containing process sign count along with sign prefixes, that large table that we just created, and send that to the worker. If we now want to process a second contact counts RDD, it'll repeat that process all over again of constructing the closure of the function along with this large call sign table. So that can be very expensive. This table is very, very large because it's being sent every time we process the file. As an alternative, all we have to do is add the broadcast, Spark context.broadcast to our load call sign table to create a broadcast variable. And then when we want to invoke it, we just simply use sign prefixes .value. Now our table is only sent once to the workers and will be reused every time we want to look up a different contact counts RDD. Accumulators are variables that can only be added to by an associative operation. They're used to very efficiently implement parallel counters and sums, and only the driver can read an accumulator's values, not the tasks. Here's an example. We create an accumulator and set the value to 0. We then take an RDD consisting of 1, 2, 3, and 4, and we're going to run a for each function against it. That'll apply the function to each of those elements, and it'll do that at the workers. The function we define is to take the accumulator and add the value to that accumulator. When we run this, we can then see that the value of the accumulator will be 10, because at each worker, we will add the value of the element. In this case, we start with 1 at the first worker, 2 at the second worker, 3 at the third worker, and 4 at the fourth worker. Each of those adds up to 10. Here's an example where we're going to count empty lines in a file. So we start by creating an RDD from that text file, and we have an accumulator that is set to 0. Now we're going to extract call signs from that file, and we're going to reference the accumulator blank lines. And if the line is empty, we're going to add 1 to that accumulator. Otherwise, we're going to return the value of splitting that line. Now we can take and create a new RDD call signs by flat mapping that file RDD that we created by passing in the RDD function extract call signs. Each time extract call signs runs against an element, if the element is blank, it's going to add 1. If it's not, it'll return the value of splitting the line. Flat map will then turn that into separate elements. At the end, we can print out the accumulator at the driver, blank lines, and we'll see what the value is. Now, tasks at workers cannot access an accumulator's values. Tasks see accumulators as write-only variables. And accumulators can be used in actions or in transformations. In an action, each task's update to the accumulator is guaranteed by Spark to only be applied once. When you perform transformations, there's no guarantee, because a transformation might have to be run multiple times if there are slow nodes or a node fails. So you should only use accumulators for debugging purposes when you have transformations. Accumulators support the types integers, double, long, and float, and you can also create accumulators with custom types. We use one of those in one of the labs. So in summary, when you write a Spark program, you use the master parameter to specify the number of workers. When you create an RDD, you can specify the number of partitions for that RDD, and Spark will automatically create that RDD spread across the workers. When you perform transformations and actions that use functions, Spark will automatically push a closure containing that function to the workers so that it can run at the workers.